We are a group of mechanical engineering students from the University of Texas at Tyler, and we're going to be discussing our design for a shell and tube heat exchanger for a low power solid state oxygen supply system. First, we will discuss why the oxygen supply system needs a heat exchanger. Second, we will discuss the specific design parameters that our project needs to address. Third, we will discuss possible design options and how they fit with our design parameters. Fourth, we will discuss our proposed solution. And lastly, we will discuss expansion issues that our solution might need to address.
For this oxygen supply system, the necessity of a heat exchanger is quite clear. This system intakes air at atmospheric conditions and heats it to a predetermined temperature necessary for a reaction within a ceramic transport membrane. Once the air reaches the appropriate temperature, it causes the air to diffuse into pure oxygen and oxygen-depleted air, which flow from the CTM to two separate outlets. The main goal of the heat exchanger is specifically heat exchange from the outlet air from both outlet channels to the incoming atmospheric air at the inlet. The optimization of the heat transfer between the outlet air to the incoming air will result in an increased inlet temperature of the incoming air as it flows through the heat exchanger, gaining heat routed from both outlets. The increased inlet temperature inevitably leads to an overall increase in the efficiency of the CTM system, as less input power is required for the CTM to function as intended.
A set of design constraints were given for this project, which provided major challenges to overcome. The first of which is the high temperature difference between the hot and cold side that is compounded by low volumetric flow of the air. These two constraints alone rule out off-the-shelf heat exchangers that are commercially available. The heat exchanger is further constrained by a power draw and a size limit as well. Power cannot exceed the amount of energy saved from reheating, and size is limited to the size of a pickup truck's bed. With such a stringent set of parameters, the selection of a good heat exchanger becomes paramount. The first design to be considered for the given parameter is the double pipe heat exchanger. This type of heat exchanger is the most thermal efficient design that allows for temperature cross when designed as a counterflow exchanger. Temperature cross indicates that the heat exchanger's hot outlet temperature can be lower than the cold side outlet temperature. There are some downsides to this design, however, due to the fact that the heat exchanger's hot and cold side temperature difference is 775 degrees. This means that in order to achieve an ideal level of heat transfer, the pipes in this design would have to be very long. In order to push the desired amount of airflow through these long pipes, the fans and the pumps would have to be very powerful, which indicates a large power draw. Since the design parameter calls specifically for a low power solution, this design was deemed unsuitable for the project. The second type of heat exchanger to be considered is a cross-flow heat exchanger that has the hot and cold airflow across each other perpendicularly. This type of heat exchanger is compact with multiple plates that allows for easily modifiable design for a larger surface area that allows for good amount of heat transfer. Unfortunately, this type of heat exchanger exhibits temperature approach, which means that the hot side outlet temperature would never be lower than the cold side temperature, and that these two temperatures would meet somewhere in the middle of the temperature delta. This fails a fundamental part of the design parameters, which is why this design is also unsuitable for our use.
The benefits of a shell and tube type heat exchanger are not only statistical or numerical, but practical as well. Due to the design constraint, material availability, and budget, the shell and tube type heat exchanger proved to be ideal. This type of heat exchanger boasts high effectiveness for transferring heat from the tubing into the cold shell side. Surface area is adjustable and not an issue, as we can make the heat exchanger as small as a microwave or large enough to fit into a back of a small pickup truck. This type of heat exchanger also has very adjustable design, as we can change the number of tubes, tube passes, tube diameters, and so on, as well as the shell area and, of course, the material. Pressure drop could be a possible issue as we have many turns, bends, and corners, unless we attempt to make a circular shell design, which is a lot harder to machine. We will also have to insulate the entire box in order to keep our effectiveness high. One final drawback is that After construction and welding of the heat exchanger, we cannot adjust the perimeter without creating a new one, which will increase overall cost.
Our prototype consists of tubing and shell material which would have high thermal conductivity and could be easily purchased from public stores. The tubing consists of 60 feet coiled soft copper purchased from Granger for $40. We cut the tubing into 5 sections, using one as a testing apparatus for flow and thermal conductivity while bending the other 4 into a proper shape for our design. The tubing parameters are a 1/2 inch outer diameter with a wall thickness of 0.07 inches and a 3/8 inch inner diameter. There are 5 bends and a total length of about 11.5 feet per tube. Although this copper has a sub 200 degrees Celsius safety temperature, that temperature is more than enough for dealing with our testing, heat transfer, and flow apparatus. Our shell design had to be a strong material that would not only hold up the weight of the copper, but insulate the temperatures inside. 16-gauge sheet metal was chosen from Home Depot and was purchased due to its properties and ability to easily cut and be welded, for about $140. The shell would be shaped rectangular with a length of 22.5 inches, a width of 18.5, and a height of 10 inches. The baffles and wall would also use the same materials for the sake of simplicity, as they are more than enough to hold the pipes up as well as keep the air from moving from side to side.
Now we will discuss the expansion issues and the need for a proposed solution. Because of substantial high temperatures, we must consider the thermal expansion within the system. Thermal expansion is the tendency of matter to change in length, area, and volume in response to change in temperature. Our goal here is to account for the linear expansion of the shell and tube in the design. Different materials expand by different amounts, so the thermal expansion coefficient varies. Alpha is a material property that represents the experimental expansion coefficient and is necessary to quantify expansion. In our heat exchanger, the proposed materials in the shell and tube are steel and copper, respectively, and thermal coefficients of 12 e to the negative 16 meters per meter Kelvin and 16 e to the negative 16 meters per meter Kelvin, respectively. The design for the expansion solution is in its beginning stages and will address the issue of varying expansion coefficients between the shell and tube materials. In conclusion, the shell and tube heat exchanger is a viable part in the functionality of the CTM. Also, as stated, the heat exchanger will meet design parameters, recover heat leaving the CTM, increase inlet air temperature, and improve CTM system efficiency and power needs. Thank you for listening to this presentation.